Okay, morning everybody. I'm about to get started. So the last two lectures I gave you a bit of an introduction to amplitudes. We computed some amplitudes, in gravity. The amplitudes we computed were obviously pretty simple amplitudes. But there's a large community of people who got really good at computing scattering amplitudes. These are my friends. They're really very good at computing these things. High orders of perturbation theory. We just did 3 amplitudes, but there's a whole army of people who are computing loop level amplitudes using methods that are somewhat similar to what I talked about yesterday. So this business of factorizing amplitudes, building them up from simpler amplitudes, etc. All of that works very well. What's actually difficult at the end of the day is performing the loop integrals, which I alluded to in lecture 1, but we haven't really discussed. The topic of the next lecture is going to be, well, if you have these people, this army of people who are really good at computing scattering amplitudes, what can you do with the scattering amplitudes? Will you do anything fun with them? So I'm not really going to compute any more amplitudes. There'll be one more in the tutorial for you to compute tomorrow. But essentially for the rest of the lectures, what I'm going to do is assume that there is a lot of smart people who are feeding us information, and we can use that then to address questions that are interesting in a wide variety of domains. So obviously the focus of these lectures will be on applications of amplitudes to classical issues in gravity. And today what I want to talk about is a method of computing classical observables taking as input the scattering amplitudes. That's the idea for today and for tomorrow. So the basic idea of this method is the following. So we start by picking some observable that we're interested in. Now the observable should make sense in the classical theory. Because we want to talk about classical applications of these amplitudes. But because the computation is set up in quantum field theory, the observable better also make sense in quantum field theory. So we pick some observable that's sensible in both the classical and quantum theories. I'll call this observable O here. This symbol is not supposed to be a 0, it's an O. So we pick an observable O, which makes sense. Both classically and in quantum mechanics. Okay, so the second thing I've got to do is pick a state. I have to pick some kind of state because I'm doing quantum mechanics, using a quantum mechanical formalism. But I want to pick a state that happens to be in the domain of validity of the classical approximation. So I'll call the state psi, and I'll discuss this state in more detail in a few minutes. So the state psi has to have the property that whatever situation it describes is in the domain of validity of the classical approximation. So it's a classical approximation to the quantum field theory. I mean, we know ultimately that all our classical theories are approximations to some underlying quantum theory. This must be possible to find some states in the quantum theory that correspond to the classical. Okay. Yeah, and the third observation is my state psi here, I'm thinking of it as an initial state. Maybe I should have put the word initial here. In other words, it's some state describing the initial conditions of our classical problem. So with such an initial state in the past, the future state is given by acting on psi with the S matrix. I mentioned this in lecture 1, right? So the S matrix is the time evolution operator, brings you from the far past to the far future. Okay, so what I will then do is compute the expectation value of my observable. Those are the things that we can expect to have a classical meaning. I'll take the expectation value of the observable on the initial state. I'll take the expectation of value of the observable also in the final state and form their difference, right? Now, since the final state is given in terms of scattering amplitudes, and the initial state is just setting your initial conditions, it's inevitable that the value, the evaluation of the observable, of the change in the observable, the delta O, is going to come out in terms of scattering amplitudes. Right? This is where all of the time evolution comes in. All the dynamics is in here. So it has to be that the observable is going to be written out in some sort of formula in terms of amplitudes. So the change in the observable must be computable. Okay, so that's the basic idea. Now the story goes by the name, the literature of the KMOC formalism. So if you see that, that name, that's what I'm talking about. There's a review in one of the reviews I mentioned yesterday. Okay, so today I'm going to talk about one observable. So I'm going to pick one of my particles, particle 1, and look at its momentum. So then I'll compute the momentum of the particle in the far future, subtract the momentum in the far past. I'll give you the change in the momentum of the particle. So the change in the expectation value of the momentum of the particle is, this is called the impulse, which is the total change during a scattering event. Tomorrow I'll talk about the waveform. So I'll build on what we've done today, tomorrow, in order to discuss the waveform. Now, one thing I should say is that this formalism applies most directly to situations involving scattering. It's sort of in the name. I'm using scattering amplitudes. Scattering amplitudes are obviously set up to do scattering. So the computations I'm going to perform will always be computations of the scattering type. So I'll compute the waveform tomorrow in a scattering event as well. Now, of course, we're well aware that, in LIGO, we're interested in bound black holes or some compact objects that are in spiraling. So there is some job to be done to transfer data, transfer information from the scattering scenarios to the bound situation that's of most direct physical relevance. You could do that in various different ways. So for example, I gave you some problems in computing the interaction potential. What you can do with these scattering methods is compute the impulse. The impulse is a very clean thing to compute because it's directly given in terms of amplitudes. You can extract a scattering potential out of that. That involves some definitions. I gave you a definition, but that's just one definition. So you have to define what you really mean by the potential. So you can define a potential associated with these impulses, and then use the information in that interaction potential to discuss bound state problems. Similarly, for the waveform, the scattering waveform, you can extract fluxes, like the amount of energy that's being emitted in a post-Minkowskian expansion, and then recycle that information in a bound states setup. Now, there are caveats to that. It's not a completely trivial thing to do, and a very interesting area of research is to try and take these ideas from quantum field theory and try and make them more directly connected to the bound state. There are papers on analytic continuation of certain observables directly from scattering to bound state situations. So those are interesting papers. Mention the authors. So. continuation observables, scattering to bound. So, authors are Gregor Klein, Rafael Porto. So they have a series of things they describe. They call it boundary to bound, B2B. So that's an interesting line of research. You can also view this in the sort of rubric of this tutti frutti method, where you compute everything that you know how to compute, extract as much information as possible, and then shove it all together in something like the EOB or something like that, where you can resum things and apply it in bound state situations. Okay, so that's how we think about extracting information for genuine sort of LIGO physics from these methods. Yeah. Okay. So let's start work on this impulse in a little bit more detail. Okay, so the impulse is going to be defined by delta P1 mu as the expectation value on this state psi, the future state of the momentum operator P1 mu, minus the initial value. So I could then rewrite this as the expectation value of S dagger. Yeah, so in here, I could insert S dagger S. S dagger S is 1 because the S matrix is unitary. So it's free for me to put in here S dagger S. And then I can realize that, well, there's if I've inserted S dagger S here, there's a psi S dagger in both of these formulae. And in the second term, P1 and S is in one order in the first term and in a different order in the second. So in other words, I can rewrite this as a commutator of the momentum operator of particle 1 and the S matrix on psi. Okay, so this is a nice little formula for what this thing is that we're actually going to compute. Now, a quick remark here. So it is the case that the total momentum operator commutes with the S matrix. So the total momentum operator is the momentum operator of all of the fields that you've got in your problem. So in our situation, I'm thinking about taking particle 1 and 2, as we had before, scattering them into particle 1 prime and 2 prime. The force will be mediated by something, gravity, for example, or electrodynamics, if I'm doing charged particle scattering. So the momentum operators then will be the momentum operator of particle 1, the field of particle 1, the momentum operator for particle 2, and the momentum operator for the force carriers, the photons or the gravitons or whatever it is that you've got in your problem. Now, the sum of all of these momentum operators always commutes with the S matrix because of translation invariance. So we can rely on this. But the momentum operator of one of our fields definitely doesn't have to commute with the S matrix, because physically you can send momentum from one particle to the other, right? But this commutator won't vanish, but this commutator would certainly vanish. And it's good to bear in mind that this is true. You're always going to have total momentum conservation. Okay. So now in this formula, we can write the S matrix as 1 plus IT, as before, so T is a transition matrix. Then the change of particle 1, delta P1, impulse in particle 1 will be, well, it's going to come out in terms of two terms. So in this, if I replace S here by 1 plus IT, the commutator of the P with the 1, that's certainly 0, right? So I could just shove in IT here instead of S. But this S dagger here will be 1 minus IT dagger. Both of those terms will contribute to the impulse. So we'll have a formula that involves two terms. So there'll be the term where I replace S dagger with 1. That's going to look like this. And then there's the term. And then there's the term where we put in the IT dagger. Okay, so that's it. So that's the total formula for the impulse. It's always got these two terms. Okay, very good. So now to make progress on this, our next step is to understand what the state is. What kind of state should I choose? I told you that I want to pick a state that's in the domain of validity of the classical approximation. So let's go into the details for that. All right, so to define the state, we just need to think a little carefully about what the object we want to compute really is. I'm going to take two particles, two distinguishable particles, so two totally different particles, different masses, and scatter them. Scatter two distinguishable. Now, I want my particles to be separated in the far past. Just a second. So I'll take them to be far apart in the far past. Two distinguishable, well separated. I want to give them different masses. I really just want these particles to be totally different. Okay, yeah, you had a question. No, so the i's cancel here. So we need an I there, but in this second term, there is an I from IT here, but there's also a minus I from minus IT dagger. So that's where the i's go. Okay, so yeah, so this is the situation I want to consider. Now, in part that's because I want to think of my particles as being black holes. So now I'm thinking of the black holes as being point-like black holes. I'm doing some sort of, you know, if you want to think about it as an effective field theory description, you know, whereas the black holes have all sorts of, you know, interesting aspects to them. But from a long distance perspective, they're just point particles. I mean, actually, they're very good point particles. That's the whole point of the no-hair theorem. So you have to go to quite high orders of perturbation theory before you see these things actually have well, properties that we don't usually ascribe to point particles. Okay, so I want to, you know, so this is why I want my particles to be distinguishable and have different masses. They can be just whatever black holes they want to be. Okay, I'll say a little bit more about some of the approximations in a little while. Okay, so the picture then, the scattering will look a little bit like this. So I'll take a particle 1, I'll shoot it in with a momentum P1, which I'll say is mass 1, proper velocity U1 mu. And there will be a second particle, momentum P2. And they're going to be separated in the far past by, well, in particular by an impact parameter. Of course, there's also going to be, you know, they're coming in from different directions, so they'll be you know, far apart in this sense, but I'm going to introduce an impact parameter which will separate them as well. So the impact parameter is just a transverse separation between the two particles. So this impact parameter will always satisfy, or we can choose it to satisfy b.u1 is 0, is b.u2. So it's a spatial separation, and if the particles are moving in, you know, the x direction, something like this, well then my impact parameter will be in the yz plane. So it's sort of a two-dimensional thing, separating the particles. Okay, now classically, these particles will have precisely defined positions and momentum. So there will be exact positions of momenta of both particles. In the quantum mechanics, as is well known, we can't have exact positions in momenta. But what I can do is I can arrange that the uncertainty in the positions of the momenta are very small compared to the scales I'm interested in. So I will choose a state psi, which is the property that the uncertainty. So I can choose that the uncertainty and the position of the momenta are very small compared to classical scales of interest. Okay, so the picture in this sense is I'll take my two particles. They're in wave packets. So wave packets have the property that they have a certain size. So I'll say that the size of my wave packet is given by some length scale. Position space size of the wave packet is given by some length scale LW. And I will separate my particles by some big distance B. And if LW is very small compared to B, I can compute my observables. They'll come out involving LW and B, and I will expand in the small ratio LW over B, and I will ignore all of the terms that have LW in them. Right? And the terms that are left around should be the classical terms. That's the basic idea. So we'll say that there's a wave function spread. LW, and that's in position space, as I've drawn the picture. It can be useful to have a rough idea of what these wave packets look like. Now, we won't care what the wave packets are like. I mean, we're doing, we're trying to extract classical physics. Classical physics shouldn't care about the shape of the wave packet of the particle, right? But to have a sort of an idea in mind of what these wave packets could look like, you can think of them as being something like Gaussian wave packets. Right? So then the position space wave packet will look something like this. Our particles will have some position. There's some central position of the wave packet, and then there's going to be a 1 over LW squared, right? So that's the size of the wave. Okay, so that's the position space wave packet, but we also care about momenta. So to worry about the wave function spread in momentum space. So that looks like h bar over LW. So notice I'm not setting h bar to 1 here. So the Fourier, you get the momentum space wave packet by Fourier transforming the position space wave. The momentum space wave packet then will look something like E minus P star squared h bar squared over LW squared. So you see that the spread in position space is LW, and the spread in W squared over h bar squared. The spread in momentum space is h bar over LW. H bar is not 1 in this lecture. So I'm keeping the h bars around because I want to explain to you, how they go away in the end. Okay, so very good. Now, I want my wave packets to have the property that the uncertainty is negligible compared to the classical scales of interest. So in particular, I want the wave packet spread to be very small compared to classical scales of interest. The spatial scale I have of the classical problem at this stage is just B. So LW better be very small compared to B. Now, when the particles scatter, they're not always going to stay, a distance b apart. I mean, the scattering is attractive, they'll get a little bit closer together. So I'll introduce a scale LS. So LS, I think about it as being the distance of closest approach during scattering. Now, if the scattering is perturbative, LS will be of order B. If the scattering, and I'm going to be doing perturbation theory, so in a perturbative situation, LS can be of order B. Yeah, I mean, it's interesting to consider situations, applications of this. The basic ideas here are non-perturbative, but the calculations I'm mainly interested in are perturbative. So I'm starting to feed in a little bit of that here. But if you wanted to consider a situation where the scattering was, strong, well, then you would just want the wave packet small compared to LS, and LS could be small compared to B. That would be interesting. Okay, but that's not the only inequality we should worry about, because I also want my momentum space wave packet spread to be small compared to classical scales of interest here. And in momentum space, there's a very obvious classical scale I care about, which is the mass. So we also need so the wave packet spread in momentum space is h bar over LW. Very much smaller than the mass. And I'm going to define the mass to be h bar over LC, where LC is some form of the constant wavelength of the various 2π's and so forth, which you don't really need to care about. Right? So this will be a second inequality of interest. Okay, there was a question. There is some wave packet spreading, yeah. Yeah, that's a good question. I mean, the spread of the wave packets is comparatively small. It's not really going to be a problem for us. I mean, one way to think about this is, yeah, I mean, I'm defining these wave packets in the far past and letting the S matrix take care of all of the evolution for us. If the wave packet spread was really an important thing in the classical physics, you wouldn't be doing classical physics. So we have to make sure, so there's a presumption here that once I've set up initial conditions which are classical in the far past, then the evolution through all time will be classical as well. Right? Now that doesn't have to be true. There are situations where it's not true. So for example, black hole evaporation. You can set up classical conditions in the far past, but in the far future, I'll get some quantum system. But in the kind of scattering problems of interest here, I'm taking two particles and scattering them off one another. I'm thinking about, ultimately using that for binary black hole physics. The evolution would be classical throughout. So then this wave packet spread can't really be an issue. Yeah. The Brownian wavelength of black hole. I would think about that as more something to do with this spread here, the quantum wavelength. Okay, very good. So we have two inequalities here, but we can put them together, and that's a nice thing to do. So you see LC must be very much smaller than LW just by multiplying across here. So we can combine these things to see that LC is very small compared to the wave packet spread, and that is very small compared to the scattering, LS. So this is the chain of inequalities that is relevant for classical applications of scattering amplitudes. I mean, it's maybe useful to think about these chain of inequalities as really having two sources. So one of them, and this one here, is really about the classical description. The second pair here, LW is very small compared to LS, is a point particle image. So if you want classical point particles, then you have all of these. Sometimes we call these the Goldilocks inequality. Again, it's interesting to consider situations where you mess around with these inequalities. And I think this one here is really about the throwing away quantum effects. This one here is about throwing away finite size effects associated with the fact that the thing actually does always have a finite size. Quantum particles always have to have a finite size. Okay. Now there's another way of thinking about this, which is also useful. Let's see. Yeah. So we can think about this one here, h bar over LC. Now this is equal to the mass. It is very big compared to h bar over LC, the Compton wavelength of the particle. Confusing myself. Yeah. Nope. Yeah, sorry. So h bar over LC, this one here, this is the mass. It is going to be very big compared to the h bar over LS. So I'm dividing these through here. So 1 over LS is very much smaller than 1 over LC. So this is this inequality here. Now I'm going to define this h bar over LC to be a momentum q. So the q is the typical momentum of the force carriers, or whatever is mediating the interaction. Now this is a pragmatic way of thinking about it. This q is very much smaller than m. So this is a pragmatic way of thinking about the computation, because when we're computing in amplitudes, we have momenta of intermediate particles, q's. We've seen those in the scattering amplitudes we've already talked about. The momenta of intermediate photons or gravitons, etc. So the momenta of those guys is going to be very small compared to the masses of the particles, the momenta of the point particles, the p's. The scale of the momentum of our point particle is p, and p is going to be much bigger than q. So in the scattering amplitudes themselves, they come out in terms of p's and q's, so I'm going to expand those. So that's actually a handy way of actually implementing the this classical limit in practical calculations, but I think the physical intuition is maybe expressed more clearly in this. Okay. Yeah. So maybe some comments on this. As I mentioned, the particles I'm talking about, I'm thinking about, I want to talk about black hole scattering. I'm approximating my black holes as point particles. That is a very good approximation, but if you want to include finite size corrections, say you want to talk about neutron stars, you want to put in some tidal deformability. There are ways that you can include those. You include them, essentially as a perturbative interaction in the scattering amplitudes themselves. So there are vertices, Feynman vertices associated with these finite size effects, which you can understand from an effective field theory point of view. So if you want to include them, that's fine. You can go ahead and compute them, people have. Yeah, so another comment. In gravity, there's another mass scale that we're very familiar with. That mass scale is the Schwarzschild radius, right? 2gm. So you might wonder what goes on here if you include that mass scale in the problem. Now, so the Schwarzschild radius so RS is 2gm. So if we want to include that in these inequalities, well, then the Compton wavelength should certainly be smaller than the Schwarzschild radius. We need this Compton wavelength very small compared to the size of the wave packet. To my mind, it's good if the Schwarzschild radius is larger than the wave packet of the object you're talking about, and this should be very small compared to LS. So this is, if you want, this is very safely classical, in that any quantum effects are already shrouded by the horizon. But honestly, I think you could, I'm not so sure. I think this inequality here, they should be, I don't think you'd want a situation where the wave packet size was somehow huge compared to the Schwarzschild scale. That doesn't sound like classical black hole anymore. So, but I mean, if they're comparable, maybe that's fine. Maybe even that's physically relevant. But certainly, if you arrange your parameters so that the wave packet's inside the Schwarzschild radius, well, then everything's fine. Yes, so in electromagnetism, there is also a scale. It's the friend or the electromagnetic version of the Schwarzschild radius. So in electrodynamics, you have a classical length scale. So the classical length scale is the classical size of the electron, which is E squared over 4 pi m, or charge squared over 4 pi m. So this was the thing that would play the same role as the Schwarzschild radius, essentially, effectively, in classical electrodynamics. And this is certainly the case that you want, so in classical electrodynamics, the interesting thing that happens, I guess, is that that length scale is actually small compared to the quantum scales. So in classical electrodynamics, well, in electrodynamics, the quantum effects come in before you start seeing these classical effects, which is one way in which electrodynamics is safe from singularities. Yeah, and a last remark. So going back to this comment here, so I mentioned that the total momentum commutes with the S matrix. That in particular guarantees that energy and momentum are going to be conserved in the problem. So there was always going to be balance, like energy and momentum will be balanced in the classical problem. As a result, this is just because quantum field theory has been set up from the start to include radiative effects. That's what people cared about when they were designing quantum field theory. So in particular, it means that when we compute the impulse using quantum field theory, effects associated with radiation reaction, et cetera, will automatically be built in. So they will always be there. There will be some loop diagrams that take care of radiation reaction for you. You don't have to go ahead and do something funny to put it in. That's one aspect of the quantum field theoretic setup. Okay. Any questions on that? How do we decide what LW is in computation? Well, we just, we don't really decide what it is so much yet. We just set it up so that it's small compared to the scales that we care about. So the formula in the end of the day, so I'm going to go through some discussion of it now in a moment, but the formula in the end of the day, this will drop out. So it's not going to be there in the classical, the final classical expression. You wouldn't expect it to be because, classically, the objects were point-like, and all details of the wave packet should be gone. So they'll disappear. Okay, so yeah, let me introduce some notation so that we can actually go through the steps to see what the expressions look like for this impulse. And we have a formal expression there, but we want something that we can actually compute. So I'll introduce wave packets. So I'm going to write them in momentum space for each particle. And then the state will be, so you can express it in terms of wave packets. Now, so I'll write the state in terms of plane wave states and be integrated against these wave packets. So we'll have these states P1 and P2. I want to integrate over the momenta that are in the states and these wave packets. That integration is going to be the same kind of integration we've already seen. So an integration over the momentum of the particles, but the particles have to be on shell, the energy has to be positive. So in other words, the measure of integration is going to be this d phi thing that we had in the last lectures. So I'll integrate over the momentum of particle 1 and particle 2, d phi of particle 1 and particle 2. One thing to be aware of, right, is that the d phi for particle 1 has a delta function setting p squared, p1 squared is m1 squared. The d phi for particle 2 sets p2 squared to be m2 squared, right? So I'm always sort of indicating that by the number on the momentum, right? Sort of an abusive notation if you want, but it's anti-shorthand. So now there's 2 wave packets for each particle. Right, 1 wave packet for 2 particles would be wave. There's these wave packets. And I have to translate one particle with respect to another. And then put in the plane wave state. So this exponential here is the thing that takes care of the translation of particle 1 with respect to particle 2. And it introduces this impact parameter, P. This is just... So I'm exploiting the fact here that the momentum is the generator of spatial translations. Exponentiating that generator gives you a finite translation. And the parameter of the translation is the impact parameter. Okay, now it's convenient to write these wave packets just as 5 P1, P2. That's just as shorthand. It infers there's, it makes some sense to split the wave packet into 2 factors, 1 for each particle, but it's possible that the particles will be somehow entangled. There's just 1 wave packet. Not a big deal, but for me, it's a convenient shorthand notation. You just said there's 1 phi for both particles. Okay, so that's the state. And now basically the job is to insert this expression, the state, into this formula for the impulse, take advantage of the inequalities that define the classical limit, and extract an expression that actually is valid in the classical approximation. Yeah. Yeah. Well, yeah. Could answer that question. I mean, yeah, the answer is that, yeah. In a sense, that the problem here is a problem of notation. So the P that I wrote over here is the expectation value of the momentum on the wave packet. That's really the classical momentum. The thing I'm integrating over in my wave packet is the thing I'm integrating over the wave packet. So to get the expectation value of the momentum, I have to take the momentum operator and take its expectation value on this wave packet, and then it'll come out as being something. So you could call that P star or P classical, right? And then this is really P classical that has this property, and in particular, there's some dot product here for P classical. Now, I don't want to introduce a separate notation for it because, you know, then there's lots of different notation. I'll have some notation in a little while that helps you understand when it's classical, when it's not. But for the moment, the reason for the question, you know, which is a perfectly fair question, is because the notation in this pane is different to the notation I've just introduced over. Okay, yeah, thanks for the question. That's really useful. Okay, so let's talk then about getting you know, an actual formula for the impulse from amplitudes. All right, so what I mean now, so what I'm going to do is take this delta P and insert that expression for psi, and then we'll go through some analysis to simplify it. So first of all, just inserting the psi in delta P, there are going to be various integrals. Now, notice that there's two psi's, right? There's the ket form of the psi and the bra form of the psi, right? And I have to integrate over momentum in all of them. Right? So we're going to have 4 momentum integrals. There's 2 here in the ket and 2 more in the bra. Here? No. So you might think that I should translate both particles. So I could write e to the I b1 dot p1 plus e to the I b2 dot p2. That would translate 2 particles. But I've just put one at the origin and translated the other one. Then it's just one translation operator for one particle relative to the other. So now this does break a certain symmetry, and I will pay a price for that tomorrow. But today it's simple as just to translate one with respect to the other, and I'm going to stick to this notation throughout. So, but you will see tomorrow. Maybe I'll mention it. I think I'm planning to mention it that at one point you'll see it looks a bit funny, and it's precisely because of this choice. Okay, so yeah, so I'm inserting my psi and the bra and the ket. Each psi comes with 2 integrals, so I have 4 integrals to do. D phi. So the ones in the bra, I'll put primes on them. The one in the ket, I write with no primes. And now you can see why I actually cooked up this d phi notation. It is very handy to have a place to put all 4 of these momenta together. That's really its reason, its job in life. Excellent. So I'll put it in here. We have a wave packet phi star. And a wave packet from the ket. There's an exponential from the bra and the ket. Now the bra is always the complex conjugate of the ket. So I will have e to the I b dot p1 minus p1 prime over h bar. So 1 from the ket, 1 from the bra. Comes in with the minus sign. Very good. So everything else I have are just these P1s and P2s. I will need a little bit more space. So there will be P1 prime, P2 prime. Right, so these are the states and the bra, this one here. Well, maybe it's most useful to use this form of the expression. So it makes it a little longer. P1 mu I t plus t dagger P1 mu t P1 P2. Okay, so that's the object that we have to simplify. Okay, let's simplify this in steps. So there's, it always has the property that it's 2 terms. So there's the first term here and the second term. So for the first term, so the first term involves, well, a P1 and an IT. So yeah. So the ket form here, I do like this. P1 prime, P2 prime, P1 mu IT, P1, P2. So this thing will equal I. See the operator P1 I think of the commutator as 2 terms. There's a term where the P1 is on the left. So that gives you a P1 prime, mu, P1 prime mu. And then there's a term where the P1 is acting on the right. That's a P1 mu. And then what's left is just the amplitude, right? So it is a t between P1 prime, P2 prime, and P1, P2. That is the 4-point amplitude. Or P1, P2 goes to P1 prime, P2 prime, times the 4-dimensional momentum conserving delta function. So that's what we get from the first term. There was a question. So it's just notation. So the question is, why am I putting primes in the variables in the ket, no primes in the variables on the, sorry, yeah, it's on the bra actually, yeah, no primes in the variables in the ket. So it's just a choice of notation. These are all variables of integration, so you can call them whatever you want. The reason why I'm putting primes and no primes is because if I put primes here, it kind of looks like a final state, and this kind of looks like an initial state. So then the amplitude, so particularly here, I've got a P1 prime, P2 prime at T, and a P1, P2. That looks like an amplitude. I mean, it is an amplitude, but it makes it look like P1 and P2 are somehow the initial state, and P1 prime and P2 prime is the final state. It looks a little like that. But they're both initial states. That's exactly right. And that's actually kind of important. So the notation is maybe a little bit misleading, because I'm kind of thinking, oh, look, it just looks a little like initial to final. But it's absolutely right that, they're both initial states. This is an expectation value. So that then leads to various interesting connections. So although I'm writing things in terms of scattering amplitudes, which are sort of in-out, initial state to final state, the observables we're really computing are in-in, so they're expectations on initial states. So what I'm doing here is I'm writing in-in observables in terms of in-out quantities. And that in itself is somewhat interesting. There's connections to Schwinger-Kaldische approaches to quantum field theory, if you're familiar with things like this. This means that there's interesting relations between the kind of propagators that we get. So because I'm writing everything in terms of amplitudes, we will have Feynman propagators everywhere, but nevertheless, the results that come out will be appropriate for retarded boundary conditions initially, appropriate for in-in situations. But that's all quite interesting how that works. So it's a good question. Yes. Star. Ah, yes, thank you. It should be. Thanks. Excellent. Okay, so that's the first term simplified a little bit. Now we're going to simplify these things a bit further, but that's a start. The second term, yeah, no, I'm just evolving forward in time. So I'm not really going to do Schwinger-Kaldische, but it's possible to set these things up so it looks very much like Schwinger-Kaldische, but I'm not going to do that. So yeah, so all of our time evolution is just in the S matrix. Or just, yeah, we just go forward in time once. Very good. So the second term here is this term. It involves P1 prime, P2 prime, T dagger, a commutator of P1 mu and T, and P1 P2. Okay, now I would like to write this out in terms of amplitudes, but sort of similar to what I did here. So here there was a T matrix between bras and kets. I can't do that immediately because I've got two T dagger, two T's. Okay, one's a T dagger. It's not a big deal. It's complex conjugate. But in particular, they're multiplied together. So what I'm going to do is insert a complete set of states, and I'll insert the complete set of states here between this T dagger and that commutator. So then I can write everything out in terms of amplitudes. The result will be a longish expression. So in order to insert a complete set of states, I'll write a sum over some states x. Right? And I'm going to have an integral over massive particle states. So I'll introduce an integral over more massive particles here. Yeah, it might be useful really to draw the picture of what I'm doing. So the picture is going to be there's states P1 and P2 coming in. Uh, there's going to be some T blob associated with this commutator. Then a complete set of states, P1, P2. Now, I'm assuming that in my scattering event, my particles don't disappear. So these are two distinguishable particles. They don't annihilate one another into nothing, right? I mean, these are two different black holes. It's not electron-positron scattering. So in particular, my black holes are in the complete set of states that I insert here. So I'm going to call those these p-twiddle variables. Then there's another t associated with this, and particles flying out p1 prime, p2 prime. So that's just reading this this object here. So the states x then will be any kind of light particles, massless particles. I mean, I'm in a situation here where I've got my two heavy particles and gravitons, so I can have any number of gravitons in this state x. I'm assuming that I always have my massive particles running around. So that's why I've made those massive particles explicit here. And the sum over x is just whatever else is running around. Okay, so then there will be, well, let's write out what the expression looks like. The T dagger matrix. My complete set of states, which will be p twiddle 1, p twiddle 2, x times. So this here is inserting unity as a complete set of states times, well, now there's a momentum operator P1, which is acting in two ways. So in one term, it acts on the P twiddle 1. So I can pull that out as I did here. So there will be a factor P twiddle 1 minus mu minus P1 mu. Okay, so that deals with the commutator and this P1 operator here. So the P1 operator gives a P twiddle 1, this one, minus from the other term P1. Okay, so that's what the second term looks like. So, and you can see, you know, so the picture corresponds, you know, you always read it backwards. So P1, P2, the T, the complete set of states coming out, complete set of states going into a second T, and a P1, P2. This is really a T dagger. And again, you know, take the picture with a grain of salt, because really it's both of the states, the ones that look like a final state is also still an initial state. But I'd have to have anti-black holes. I definitely don't want to do that. That's very much not a classical process. So I'm assuming that the energy I'm scattering these things at is low enough that I don't have black hole particle production. You know, I don't have any, you know, yeah. So, yeah. I mean, in fairness, I mean, I can give these things a quantum number that would keep them safe from annihilation. I mean, they have different masses. I can't annihilate them against one another. They're not going to go away. It'll be 2 plus n. Yeah, it's 2 plus n. Yeah. Well, there would be if I wrote it in terms of amplitudes, but as t's, they're just t's. So indeed, it is good to write it in terms of amplitudes. So you want to take it, I'm not going to take this much further, but if you want to, you know, so well, I'll make some further remarks about it, but I'm not going to simplify this much further in front of your eyes. I will write a final answer for it, but it takes a little bit of analysis. The notation? Uh-huh. So you're talking about, well, I mean, there is indeed always a long-range interaction between these two particles. There will be, so even in electrodynamics, people talk about this as Coulomb phase or something. So there's always some interaction with them, no matter how far apart they are. That's true. That leads to issues when you're computing scattering amplitudes. The issues are associated with infrared divergences, but they're rather well understood. If you compute these amplitudes in the standard way, you will incorporate all of the effects associated with long-range interactions. It is particularly nice, the momentum transfer is a particularly nice observable in this sense. So there are certain other observables which would be more difficult to treat. For example, the positions of the particles. If I tried to talk about where the particles really are, well, that actually goes to infinity. So their separation would go to infinity, et cetera. So there will be specific divergences that are more tricky to deal with for those kind of observables. But for the momentum transfer, this impulse, it is a property, if you want, that it is infrared safe. So these issues aren't incredibly relevant. The issues are more thorny for the waveform. I don't think I'll have much time to talk about it tomorrow, but there is an infrared effect in the waveform that requires some study. It's understood, but it leads to a divergence in the waveform. So divergence can be removed by a shift of one of the variables. It's quite well understood, but it is an effect that's there, or a phenomenon that's there, and it has physical importance. Okay. Now, so let's think about what this impulse looks like in order by order in perturbation theory. So at lowest order, we're just going to have this term here. So lowest order in perturbation theory, so for example, if we think of electrodynamics, the 4-point amplitude at lowest order is the 3 4-point amplitude. It's order E squared. This object, this term here, if I thought about putting in, what is the lowest order it can contribute? Well, it would be the lowest order amplitude here, which is order E squared, and the lowest order amplitude here, which is also order E squared. So this term only contributes at order E to the 4th. So at lowest order, I just have the first term. So it's a tree computation. So the next leading order impulse. Well, now at lowest order, in the first term, you'll need to include the one loop correction. So in terms of perturbation theory, this will be order E to the 4th in electrodynamics. So there will be an A4 one loop. Let me write it like this: A4 1, so 4-point amplitude, one loop. So this is the first term. The second term will now contribute. It'll contribute like this. So there'll be so I'll have to insert the tree-level amplitude here at lowest order, and the tree-level amplitude here at lowest order. And then I'm integrating over this intermediate set of states here. So people usually think about it like this. So it's a tree amplitude times a tree amplitude. The intermediate legs here, these p twiddles are attached to both sides. They don't really make a loop, but you integrate over them in a certain way. And that is connected to a loop computation. And the specifics or technical connection is if I take a loop computation, take its imaginary part, it happens that will replace a standard loop integral with this specific on-shell momentum space integral. So this the second term, when it contributes first, contributes in a way that's related to a 4.1 loop amplitude. So it's called a cut of a 4.1 amplitude. Maybe it's better just to draw this as the actual amplitude that would contribute. So something like this, that thing. And then, so it's a product of these two things, and so this dashed line here is indicating that these legs are combined in some particular way, but with this integration, not a loop integration. So this is called a cut one loop amplitude. So cut one loop amplitudes have the property that they're integrals over tree-level amplitudes squared. So the basic story is that this next to leading order impulse is computed ultimately by a 4.1 loop amplitude on this object here, which you can actually extract from a 4.1 loop amplitude. So ultimately, it's all a 4.1 loop computation. Then if I were to go to higher orders, let's say next to the L orders beyond leading order, well, then the ingredients would be an L loop amplitude from the first term. And in the second term, you will get, again, it's maybe amplitudes technology, which I haven't defined, but the cut of a 4-point L loop amplitude in the second term. The point I'm really trying to emphasize here is that no matter what you do, it's always 4-point amplitudes, and you have to include loop amplitudes. They contribute classically. Sometimes people think that loop amplitudes are not classical. It's context dependent, let's say. There are certain theories where loops aren't classical. There are certain theories where there are. In this particular setup that I'm thinking about here, where I have scalar fields coupled to gravity, then the loops can contribute classically. I'm coming to it. Okay, good. Yes, that's loops will carry H bar. Yep. I'm coming to it. You'll see more about it. So there, I mean, it's an interesting story, and I will discuss it before the end of the lecture. Okay. All right, so what I want to do now is focus on the leading order impulse. At leading order, delta P1 mu. So let's assemble what we have here. So I have still quite a bunch of integrals to do. We've got our wave packets. We've got our impact parameter. That's got a H bar in it. It's this translation operator times. So this contribution from the first term. The amplitude, let me just write it as A40. It's the tree amplitude for this process. I won't write it in the amplitude. And delta functions. Okay, now I want to simplify this integral, and I want to actually start to take the classical limit. Okay, so we get an actual explicit expression that we can easily compute. So I'm going to simplify it in the following way. So the basic idea is I'm going to do some of our integrals with this delta function. Then I'm going to perform a change of variables that will make one of the other integrals a little bit more transparent. The picture is going to be that the particles come in, with the caveats we've already discussed, momentum P1, P2. So far I'm thinking about this outgoing particle as having momentum P1 prime, but I'm going to choose that its momentum is given by P1 plus Q. Q is going to be a variable of integration. And then by momentum conservation, this guy is going to have momentum P2 minus Q. So the way I'm going to achieve this is by doing one of the integrals. I'll do the P2 prime integral with this delta 4. And then I will do a change of variables for the P1 prime integral. So then this delta P1 mu at leading order will be given by, I'll still have integrals over the phase space, the momentum, the unshell momentum of particles 1 and 2. I'm going to do the P2 prime integral against this delta function. Right? So then P2 prime is equal to P1 prime, well, whatever, P1 plus P2 minus P1. Then I'm going to define P1 prime to be such that I'll introduce Q so that P1 prime is equal to P1 plus Q. So I'll have an integral over Q left over. That'll be the remainder of the P1 prime integral. So I have a Q integral to do. Very good. Now I have to be a little bit careful because the P2 prime integral, I did it with the delta function. But d phi of P2 prime has a theta function in it telling me that the energy of P2 prime should be positive. And also a delta function, a one-dimensional delta function, then that P2 prime squared is m squared. So there's going to be a delta function here, one for P2 prime, also one for P1 prime. Now those delta functions, all their job is to say is that this state and this state are on shell. So the delta function for P1 prime will be delta, say P1 plus Q squared is m squared. But P1 squared is already m squared. So the delta function will set 2P1 dot Q plus Q squared to 0. And similarly for P2 prime, P2 dot Q minus Q squared, that has to vanish, times. Now there's the theta functions for positive energy. So there'll be a theta function saying that P1 0 plus Q 0 is positive, and a theta function saying that P2 0 minus Q 0 is positive. Okay, so that's all of these measures. There's the wave packets, phi star. So that's P1 plus Q, P2 minus Q, times a phi of P1 Q. Continue. This exponential factor will be e to the I. Now, I've set P1 prime to be P1 plus Q. So this will be e to the minus I, e dot Q over h bar, times I Q mu. Now, P1 prime is P1 plus Q, so all we're left is with the Q, times A40 of Q. And I've already integrated over that delta. Okay, now the formula still looks messy, but we haven't taken care of simplifications that we have available to us in the classical limit. So we have these inequalities over here, in particular this inequality down here. Q is very small compared to P. And I can exploit this inequality to simplify this expression down to something that's nice and neat and tidy. So that's our job now. So I want to exploit these inequalities, lead to some simplifications valid in the classical regime. So the first, let me note that Q is very small compared to P. So in particular, in these theta functions, the energy of the particle, the point particle, is big. The energy of this graviton, photon, whatever, carrying the interaction is very small, right? So I get to neglect the Q's here compared to these P's. The theta functions are just 1. So you never take away more energy from the black hole than the black hole has. So these are just 1, and we can just forget about it. So let me say, so the thetas. Similarly, in these delta functions, the Q squared term here is very much suppressed compared to the P dot Q. So there's, I mean, there's a p dot q here. Here's a q squared. Q is small compared to p, so I'll neglect the q squared in these delta functions. So I'm going to write delta function delta 2p p1 dot q plus q squared is approximately delta 2p1 dot q. And similarly for p2. Now this is a bit of a tricky one. And I'll come back to it. You need to be careful about this. There's these delta functions. Delta functions are very singular objects. So approximating delta functions is something we've got to do with some delicacy. But at leading order, this is fine. Let me just say careful, and I'll mention exactly why we need to be careful in a few minutes. But for now, it's fine. Okay. Second inequality to get to satisfy, or the second simplification I get to exploit, is exactly the one I'm about to rub out. So the size of the wave packet is very large compared to the constant wavelength of the particles. So let me maybe keep the wave packets here for a moment. Okay, secondly, so this Q is very small compared to h bar over LW. So in particular, I'm thinking about my wave packets in momentum space. So this phi, this wave packet here, phi star. Well, let's just look for particle 1. So phi star p1 plus q is going to be approximately phi star of p1. So the idea here is that the wave packet is very fat on the scale of the q. It's very thin on the scale of b, right? But it's very fat on the scale of the q. So the shift of the central value of the wave packet on the small scale is negligible. So for example, here, if we consider the wave packet as being e to the minus e plus q squared minus p star squared LW squared over h bar squared. Well, there is a term here which is q LW over h bar squared. But q LW over h bar is very small compared to 1. So this thing is, so this q here is negligible. And indeed, the corrections are exponentially suppressed. So this particular approximation is a good one. So our delta p mu at leading order is then going to take the form with these simplifications. Delta phi p1, p2, this integral here. Now the thetas are gone. This wave packet here is just phi star p1, p2 times phi p1, p2. Sorry, that's not a q, that's a phi. So in other words, we get the norm squared of the wave packet that comes out. Okay, so we factored out all the wave packet stuff in this integral. There is still this q integral here. Now these delta functions have simplified. Maybe I'll give myself a little bit more space now. I don't need these wave packets here anymore. d4q delta 2p1 dot q delta 2p2 dot q. Thetas are gone, phi's are gone, e to the minus ib over ib dot q over h bar by q mu. Okay, so it's tidying up quite nicely. Now, in particular, this integral here, now, its job in life, it's just an integral over the wave packets, right? So all it's doing, wave packets are, now I'm going to want to think about them as being sharply peaked. So all this is doing is setting the value of the p's in here at their classical value. So now I'm coming back to the comment from earlier. I have integrals over some momenta, but what they're really trying to do is just to evaluate the momenta in here at their classical value. Now, rather than introducing a notation for the classical value of the central value of the wave packet, I'm just going to write this integral in terms of an angle bracket notation. So write it like this. E to the minus I b dot q over h bar, I q mu. The job of these angle brackets is to tell you that these momenta now are the central value of the wave packet, so the classical momentum. Okay, so now all the wave packets have gone, and the formula is nice and tidy, and it should directly apply in the classical limit. Okay, now there's one thing that remains very peculiar about that. Just, I've used all of my classical simplifications. I still have h bar in my formula, so you mightn't like that. So what I want to do in the remaining 10 minutes of our lecture is explain what happens with the h bar. First thing that I can do to tidy up the h bar a little bit is just make another change of variables. I'm going to define a new variable q bar. So I will let q equal to q bar h bar. So if I insert q equals q bar h bar here, the h bars will cancel. Now q is a momentum. So it's dimension of mass. H bar is dimension mass length. So q bar is dimension 1 over length. It'll be a wave number. Q bar is q over h bar. Okay, so then delta P1 at leading order will be our angle brackets. Okay, so I'll change q to q bar, and then in doing that, I'll pick up some factor of h bar. There'll be 4 of them upstairs, but then there's 2 downstairs because I do the same thing for these delta functions. Now I'm carrying 2 powers of h bar. There's e to the minus I b dot q. This I q mu now gives me a 3rd factor of h bar. So A40 of q bar h bar. Okay, so well now, I mean, I got rid of the h bar outside of the exponent, but the price is that I've got 3 powers of h bar downstairs. So again, that might be a bit funny. So what's happening? Of course, what's happening is we haven't looked at the amplitudes yet. So let's take a look at the actual amplitudes that contributed. So let's look, for example, at electromagnetic scattering. So if I do scattering of 2 charged particles, well, then this A4 is precisely the 4-point amplitude that we've been talking about in the last 2 lectures. So we know what A4 tree is. That's A40. So it's Q1, Q2, E squared. I guess there's a 4. 4 P1 dot P2 over Q squared. Plus 1.
Gosh.
This is how I wrote in my notes. Okay, now, this is the formula in units when h bar is equal to 1. So what I really need to do in order to understand the h bars here is to restore the powers of h bar in this formula here. It's always easy to restore the factors of h bar when you know the dimensions of everything, and in particular the dimension of the thing you're talking about. So we need to know here that the dimensions of A40, mass dimension, so the angle brackets here is a dimension. So it is mass to the power 0, so it's a dimensionless quantity. There's various different ways of seeing that. So this might be a little bit unfamiliar to you. One way of seeing this is that creation and annihilation operators go like a delta phi. So that's like 2e delta 3 of p. So delta 3 of p, that's got dimensions of 1 over mass cubed. E is dimensions of energy, so this side is dimensions of 1 over mass squared. So the creation and annihilation operators themselves are dimensions 1 over mass. So the amplitude we're talking about is something we get from the S matrix. So each state is made with a creation operator, or is dimension 1 over mass. So this is dimension of 1 over mass to the 4th, but it is the 4-point amplitude times a 4-dimensional delta function. And a 4-dimensional delta function for our momentum conservation. So this also has a 1 over mass to the 4th. So they balance, and A4 has to be mass, dimension mass to the 0. Okay, so this thing on the left-hand side is dimension less. P1, P2, and Q, these are all dimension of mass, so the roundy brackets are dimension less. What about E? Here we need to remember that E squared over 4 pi h bar c. So this is the fine structure constant that appears in quantum mechanics of atoms and so forth, nuclei. So this quantity is dimensionless. E squared over 4 pi h bar c is dimensionless. When you restore h, if h bar is not 1, E squared is not dimensionless. It's dimensionless when h bar is 1, right? When it is not 1, we need to restore a h bar so that this whole thing is dimensionless. Okay, very good. Now I want this amplitude evaluated at q bar h bar, not a q. So then I should write this the h bar squared, and there is 2 more powers of h bar downstairs. So the h bar cubed here cancels the h bar cubed here, and the resulting thing starts to make sense. You see once again that this thing here, the contact term is quantum. So as I said in the last lecture, we're not going to care about contact terms. Here's why. They're quantum mechanical. This is one way to see that they're quantum mechanical. Another way to see that we don't care about the contact terms, and this is something it's worth doing in the tutorial today. I've asked you to do the integrals that appear here. So if you keep this term when you're doing the integral, you'll find that it contributes a delta function in impact parameter space, a delta 2 of b. But our whole setup presumed that the impact parameter was large compared to other quantities in the calculation. 0 is not large. So delta 2 of b, that doesn't fire. The delta function doesn't go off because b is non-zero. So that's another way we don't care about the contact. Okay, so that is the fate of the h bars. So this h bar cubed cancels that h bar cubed. That term doesn't contribute. And now the formula, it really is classical, and you can go ahead and compute it. Now, in the tutorial, I've also asked you to evaluate this formula in the context of gravity. So in the gravitational case, there's also a 4-point amplitude. That's the one that you've seen, again, with the kappa squared, which is 32 pi g. It's, if you're worried about the dimensional analysis there, it goes through in the same way. So there's also a factor of 1 over h bar in that amplitude, which comes from thinking about the dimensions of G Newton, etc., getting all the dimensions right in that formula, you'll see if you restore h bars, you got to put a 1 factor h bar downstairs, and there's 1 over q squared, so that the h bar cubed cancels at the end of the day. So those are all jobs for the tutorial. One thing I did want to mention before finishing is just what happens at one loop. So maybe I can take a moment. Is it okay to take a moment to talk about that? So I'll just be brief. I'm not planning to discuss the loop computation in any detail, but I do want to mention that some of the issues that arise, or a principal issue that arises. One loop, we would perform essentially the same simplifications. So now at one loop, there's 2 terms, but if I take this term here and just go through the same procedure, I'll just have the same formula except with 1 loop amplitude. So what about the h bars in that 1 loop amplitude? That's the first question. That's the thing I want to discuss. The last topic. So the 1 loop amplitude looks like, one of the terms in a 1 loop amplitude looks like this. So we have our P1 here. There's a loop momentum. So let's say this is P1 plus Q. Then down here we have L minus Q and a P2 minus Q. So now this integral involves an integral over L. The various propagators that appear well, there's 2 propagators for, well, let's call them photons. There's propagators for the massive particles. And they're P1 plus L squared minus M squared, but P1 squared is M squared, so I can cancel the M squared. So for this one, P2 dot L minus L squared. And then 4 powers of E, one for each vertex. So I want to count the powers of h bar here. Now, the whole thing has to be dimensionless. And there's some numerator. The numerator won't matter because it's all P1 dot P2 is a various kind. So it's dominated by P1 dot P2. There's no h bars in the numerator. There's no dominant h bars in the numerator. E to the 4th, to make it dimensionless, I should put a 1 over h bar squared. And then I remember, well, I'm supposed to make my cube be a q bar. So that has a h bar in it. So one way I could do that is I'll make q bar. There should be a h bar. I'll also make L bars. So I mean, L is kind of like a q. They're all momentum of photons. So I'll define L bar in exactly the same way. So then I can pull a h bar out of there. There's 4 h bars upstairs. There's 4 h bars downstairs. So I didn't do anything. So that's a handy way of dealing with that. But in here, there's going to be some powers of h bar, in particular from here. So this one will contribute when I pull out powers of h bar. And pulling out the h bars from these 2 propagators, I'll get 2 more powers of h bar. So there's 1 over h bar squared times 1 over h bar squared. So the whole thing turns out to be 1 over h bar to the 4th. And that's very bad because I have 3 powers of h bar in the numerator, supplied by the numerator of this formula. I've got 4 powers of h bar downstairs. That's very bad because I want to take h bar to 0 and the thing's blowing up. So people refer to this as the problem of singular terms in h bars. Sometimes it's called superclassical because it has somehow fewer powers of h bar than the classical term. My collaborator David Kossauer is very unhappy with this phrase because he doesn't think it's super at all. He thinks it's bad. Anyways. Now, all that's happened here is we've looked at part of the formula, not all of the formula. So there's the other term. So I said this 1 loop approximation, we have the first term in the impulse, this term, but we also have the second term in the impulse. When you combine them, this singularity cancels. But you have to be careful in doing that. And in particular, you have to be very careful about this delta function approximation. So you can't make this approximation until the singularity and H bar is cancelled. Because, I mean, what this is trying to do is set P1.q bar to be H bar Q bar squared. So if you apply this, this approximation after cancellation of singularities in H bar. And that's part of what's meant by this notation with double angle. Okay, so that's one of the issues. So when you actually compute this thing to higher orders, there is some work to be done. This is one reason why people like world line theories. It's a little simpler. Okay, anyway, that's all I wanted to say for today. Sorry for going a bit over.